Okay, now let me start. So x1 dot equals sum f1 of x1, x2, etc. xn. So this is an n-dimensional system where the dynamics of the state variable x1, the dynamics of the state variable x1 is related to the function of all the state variables, n number of state variables, x1, x2, etc. xn. Like that, I'm going to write others. I mean, for other state variables also, I'm going to write this equation: x2 dot equals f2 of x1, x2, etc. xn. Similarly, if it's an n-dimensional, here it's evident that it's n-dimensional, right? N-dimensional. So xn dot equals fn of x1, x2, etc. xn. Okay. Now, how can we visualize the solution for these equations, or rather the trajectories of these equations? So if there is an n-dimensional space, with coordinates x1, x2, etc. xn. So as of now, I'm not explaining this with respect to control point of view. This is just mathematics, but you can assume that these variables are the characteristic variables of the system. Okay, so the dynamics of the characteristic variables are of the concern here. Now, the trajectories of x1, x2, etc. xn. What is trajectory? Because x1 is inherently a function of time. That is why we are taking x1 dot, right? So with respect to change in time, we have a trajectory for x1 of t. Similarly, we have a trajectory for x2 of t. Similarly, up to xn of t, we have several trajectories. So this is basically when you get the solution of these equations, these differential equations, first order differential equations, then it will give you a trajectory in the n-dimensional space. Okay, so let's start slowly with the simplified case of n equals 1. So we don't have x1, x2, etc. up to n. We just have x dot equals f of x. Let's start from here. Now, x of t is a real valued function of time. This is x of t. This is x of t. X of t is a real valued function of time, and f of x is a smooth real valued function of x. Now we'll call such equations as one-dimensional or first order systems. Here, these are first order systems. First order systems. Okay. Now we can go for another analysis in the same context. We do not follow the function f to depend explicitly on time. That means our f of x is equal to x dot, but x dot we have not written in terms of f of x comma t. We have written it as f of x, where x is a function of t. Both are different. So there is no explicit dependence between x dot and t, but it is explicitly dependent on x, that's all, but x is in a way dependent on t, that's all. Okay, that is the difference. So there are two types of equations, non-autonomous and autonomous equations. So the first one is non-autonomous equation. Non-autonomous equation where x dot is explicitly depending on time. It's not autonomous to time. Okay, that is what is the meaning, non-autonomous. Now, we have considered only x dot equals fx, which is a autonomous system. Autonomous system. So for simplicity, we are taking it as an autonomous system and analyzing it. So if we are taking x dot equals f of xt, if it should be really regarded as a two-dimensional or second order system, this can be discussed later, but as of now we are discussing it as an autonomous system. Now we'll see the geometric way of thinking for these equations. let's take x dot equals fx as f of x as a nonlinear function, x dot equals sin x. Okay, sin x. Now, what is your dx by dt? Dx by dt equals sin x, implies dt equals dx by sin x. Okay, we are trying to solve for t. Okay, we are trying to solve for t. So t equals integral of cosec x dx. Now, when I am integrating it, I am getting minus natural logarithm of cosec x plus cot x plus c. Now, how will you evaluate c? What should be done to evaluate c? Anybody?
Say t equal to 0 or something, put and get.
Yeah, that is what. So for t, exactly. So we are applying the initial conditions. So for t equal to 0, let's assume that x is known as x naught at t equal to 0, because x is x of t. So x of t naught be x naught. Okay. So then we are able to evaluate c, and after evaluating c, let's take it as, I'm getting like this. Suppose t equals natural logarithm of cosec x naught plus cot x naught divided by cosec x plus cot x. Okay, now here you can see that time has explicit dependence on initial values. Initial values are this one, right? Time has explicit dependence on initial values. When you modeled linear systems in your basic control course, where you defined the transfer function and state space models, you were assuming that the initial conditions are always 0. We take initial conditions are 0, then only we model the transfer function. So the systems were, the response of the system was not initial condition dependent. The response was not sensitive to initial conditions. But when you move on to a nonlinear system, it may be dependent on the initial conditions also. That we'll see through the geometric explanations. We'll see how it is. Now, let's see another interesting thing with this solution. Suppose your x naught equals pi by 4. Describe the qualitative features of the solution x of t for all t greater than 0. What is our solution? X of t. It's a time series, x of t. So your t is now dependent on x naught, right? So when x naught equals pi by 4, you will get a particular value for t, and if you substitute t here, you will get x of t, right? Now you are changing your x naught again. Maybe x naught equals pi. So your t is again changing, right? Now you are again evaluating your time series x of t. That is your solution. Okay. If this is considered as a state variable, then the state dynamics is governed by x of t and x dot of t, right? So x of t is our solution basically. So again x of t is changing, right? So for an arbitrary initial condition x naught, what is the behavior of x of t as t tends to infinity? What is t tends to infinity? That is the steady state response. So the steady state response of the system itself changes with respect to change in initial conditions. That is what is the meaning here. So with respect to nonlinear models, we have initial condition sensitive steady state response. That is what is the meaning. Now let's see this, the same function x dot equals sin x. We'll draw it as a figure, okay, a plot. So I am going to draw this as x dot versus x. This is x dot, this is x. Slowly we'll move on to the physical characteristic here. Before moving to the physical characteristic, let's see how it can be explained. Okay, so this I am going to draw like, okay, 1 minute. Let me draw like this. I am getting something like this. Okay, oh, sorry. Okay, so this is my sin x, and you know that our function is x dot equals sin x, right? And this is x. Now we'll see. This is a graphical analysis of x dot equals sin x, and we think of ts time, ts time t. So this is x dot and this is x, but x is actually x of t. Okay, x is actually x of t. Now, when time runs or when time lapses, what happens is x is say x is the position of an imaginary particle moving along the real line. This is x. X is the position of the particle which is moving through the real axis or the horizontal axis. So what is x dot then? The velocity of that particle, right? Velocity of that particle. The particle position is changing with respect to time. Position is changing with respect to time because x is a function of time. Okay, so that is what is happening here. Physically, we are mapping this to such a context. Now, then the differential equation x dot equals sin x represents a vector field on the line, and it dictates the velocity vector x dot here. The velocity vector x dot. Okay, the velocity vector x dot to position x, right? Position x. Now we are sketching the vector field. It is convenient to plot x dot versus x like this, and we are going to draw some arrows on the x-axis here. On the x-axis, the arrows the arrows are such that when x dot is positive, the arrow is to the right side, and when x dot is negative, the arrow is to the left side. So in this segment, where should be the arrow? How the arrow should be here? X dot is negative here, right? Here the x dot is positive. I am keeping the arrow to the right side. Now here again, x dot is negative, arrow is like this. X dot is positive, arrow is like this. Okay, so this is what is happening. Okay, 1 minute, I will show you. Okay, so here we get, this is pi and this is 2 pi. This is 2 pi. Okay, now where are the points x dot equals 0? Where are the points satisfying x dot equals 0? Where are those points? Anybody? At the 0 crossing, right? These are points in which x dot equals 0. What is the importance of x dot equals 0? X dot equals 0 is the equilibrium point or the fixed point. Fixed point. That means your state variable has a dynamics. It follows a trajectory, but once it is trapped at a particular point, then even if time lapses, it does not move. Then x dot equals 0, right? That is a fixed point. Now, how will you analyze the stability of a fixed point? When you disturb the system from a fixed point or around a fixed point, then if the response moves away from the fixed point, then it's an unstable fixed point. Or if you disturb the system from some fixed point and it is coming back to the same fixed point, then it's a stable fixed point. Now here can you identify which are the stable fixed points and which are the unstable fixed points? So these are our fixed points. This is fixed point 1, 2, 3. Suppose I am marking like this, 5, 6, 7. What about fixed point 1? What happens to fixed point 1? Whether it's a stable fixed point or an unstable fixed point? Anybody?
Unstable, sir.
Unstable fixed point, because from here if we disturb the system, what happens is we are already assuming that a particle is following a path through the horizontal axis where the position x is all changing. We know that the velocity x dot is a vector. So if x dot is negative, as it is a vector, the direction reverses, right? That is why for positive x dots, we have followed a particular direction convention, and for negative x dots, we have followed another direction convention. So here we have considered for positive x dot, we take it as from left to right, and for negative x dot, we take it as from right to left. Now, this is the point at which x dot equals 0. This is fixed point. This is another fixed point. X dot equals 0, x dot equals 0. Now from here, if we disturb the system, what happens is it will go like this, or if it is disturbed in the other direction, then it will go like this. It will go away from the fixed point. But what happens if you disturb the system from the fixed point 2? If you disturb the the system from the fixed point 2, what happens is it is disturbed, but the direction is again this one, because x dot is negative. So the velocity vector is negative, right? So it comes back. From here also, if it is disturbed in the other direction in the sense towards this. This is one direction, this is another direction. In both direction, if it is disturbed, its velocity reverses and it tries to comes back to the same fixed point. So this is basically a stable fixed point, and this is an unstable fixed point. Okay. Now, what is the importance of this stable and unstable fixed point? We'll see. Once again, I am going to reiterate this. So there are two kinds of fixed points in this figure. The fixed points 1, 3, 5. They are unstable fixed points. The fixed points 2, 4. They are stable fixed points. Okay. Now, the stable fixed points are often called as attractors or sinks because it attracts to the same point, right? You can see here the fixed point 2 attracts to the same point. Now, the other fixed points, the unstable fixed points, are also known as repellers. These are repellers. These are attractors. Okay, attractors. Now with this picture, we can now understand the solutions to the differential equations x dot equals sine x. Again, we are moving back to x dot equals sine x because what we have plotted now is x dot equals sine x. The graphical analysis is between x dot versus x. Okay, so we just start our imaginary particle at x naught. Some x naught, I am going to start my imaginary particle. So that is the initial condition, basically, right? And watch how it is carried along by the flow. Flow is through the horizontal axis. I'm going to see that. So let's play with the particle with the initial condition x naught equals pi by 4. X naught equals pi by 4 in the sense somewhere here, right? Somewhere here. What happens? Starting at x naught equals pi by 4, it moves to the right. The particle moves to the right faster and faster until it crosses x equal to pi by 2, right? X equal to pi by 2. What happens after x equal to pi by 2? For sine x, what happens? X dot is your velocity, right? Velocity is seen decreasing. That means it is decelerating. The particle is decelerating. So till this point, it moves faster and faster, right? From pi by 4, if it starts, it moves faster and faster, and after this point, it decelerates, right? Until it crosses x equals pi by 2, where sine x reaches its maximum, it moves faster and faster. Then the particle starts slowing down and eventually approaches the stable fixed point at x equals pi. Stable fixed point at x equals pi. From the left, it reached from the left. Okay. So this is one qualitative form of solution. Analyzing this graph. Now, let's see the curve. Let's see one curve in which here I'm going to draw another curve. This is t versus x. This is basically the time series of x of t. Okay, t versus. So from pi by 4, I am starting. X naught is pi by 4, right? I am starting from pi by 4. This is pi. This is my pi. So initially your speed is very high. Later, after pi by 2, your speed is decreasing. The particle speed is decreasing and slowly it reaches pi. And at x equals pi, here x dot equals 0, which is a fixed point, right? Which is a fixed point. So this is how we get. So the curve is concave up at first and then concave down. And this corresponds to the initial acceleration. This corresponds to initial acceleration where x less than pi by 2. Then after pi by 2, here, this is x greater than pi by 2 and 2 pi till pi. Okay. So the deceleration towards pi. Deceleration towards pi. Okay. Now the same reasoning applies to any initial condition x naught. So now we can see if you change the x naught from pi by 4, your particle is starting from another point. The particle heads to the right and asymptotically approaches the nearest stable fixed point. Similarly, if x dot less than 0 in the sense the velocity vector is changing its direction, x dot less than 0. Okay, initially the particle approaches the nearest stable fixed point to its left. If x dot equals 0, then x remains constant. There is no change in position. The velocity is 0. Okay, the qualitative form of solution is like this. So now we see that the systems are initial condition dependent. To explain this in detail, what we can do is we can draw another figure where this is 2 pi. Okay, this is 2 pi. So we see that this is pi. So basically pi is a stable fixed point. Stable fixed point. Now I am starting from different initial conditions. From here, if I start, it will go like this. From here, if I start, it will go like this. So basically, all these points are reaching the stable fixed point. Stable fixed point, right? But the pattern you see, this is x, your x. This is your t. This is your t. Okay. Now we are starting from different initial conditions and finally settles down at some fixed point which is stable. Okay.